Okay, Ihsan,
Okay. Yeah.
whenever you're ready.
Thank you. Thank you, Edward, for the introduction. Today, I will talk about a pyramidal approach for designing deep neural networks. I will slightly introduce deep learning and why pyramidal neural network, and then I will mainly discuss two pyramidal approaches that we propose in our past work, 3D pyramidal neural network for analyzing or processing videos, as well as imposing pyramidal structure on existing deep neural networks like CNN, for example, AlexNet or VGG. And then I will conclude my presentation. To give my definition of deep learning is that deep learning is an area of machine learning that extract features or high-level abstraction from data using models composed of multiple non-linear transformation, or more formally a new area that is taking machine learning closer to its original goal of artificial intelligence. This was the first model called AlexNet that recoined or that coined deep learning word, which showed pretty good result on ImageNet dataset that was having 1.5 that have 1.5 million images of 1,000 categories. It was an enhancement of Yon-LeCun lineate model, but they have changed by changing the changes that did in it was the use of ReLU activation function, local response normalization, dropout layer, and increasing the number of layers, and more importantly, implementing this network on 2 parallel GPUs to train it on those 1.5 million images. But in this model, no doubt it showed pretty good results, and everybody shifted from traditional computer vision and machine learning towards neural networks. There was one question for most of the new researchers or data scientists, that how to design these deep neural networks. For example, if you can see here, here in C1 or layer 1, they have 96 kernels that provide 96 output feature maps. In layer 2, they have 256 kernels that give us 256 output feature maps that are as input to the next layer. And then go on, then 384 kernels and 384 kernel in layer 4 and 256 kernel in layer 5. They have increased the number of layers and the kernels in each layer, but on which basis, that is a question. So there was no proper criteria to design these deep neural networks other than the point that increased number of layers and kernels. But this also creates a problem of explosion of parameters, means that more layers and kernels you have, the more parameter you will have. And for the people who want to deploy it on edge devices or FGPA, sometimes you might have limited memory. So you want to have small or as light model you have as possible that can be easily transferred via the cloud. Another point was that these convolution neural networks was rarely changed. For example, only GoogleNet was the one who changed the structure by bringing the error calculation within the network, or network in network was slightly different. Other than that, they all use the same convolution neural network that is modeled in different ways. When you increase the number of layers and kernels, it increases ambiguity and also create convergence problem. So to find a solution for having less number of kernels, having a general criteria of designing neural networks, and to optimize it or train it quickly, we went back to find a solution and tried to search biological neurons, or the concept of biological neurons. And we found that there is no single criteria or no single structure about these neurons. There are multiple theories, but one of the idea is that neurons in biological brains work in pyramid structure. By pyramid structure, I mean that they multiple combine to give decision at the higher level. And you can also see on the right of the structure of a pyramid. This is taken from Wikipedia, all these images. Pyramid starts with a big base and then refines or reduces at each layer, and finally a decision is taken. So we took this idea, which was also being used in traditional computer vision and machine learning. For example, if that's the main idea, if you have more features, use a feature subset selection technique to reduce them and then give it to a classifier so that it can classify it correctly. So a general criteria is the objective for new researchers to design networks to reduce the parameters in these deep neural networks and to reduce ambiguity with this pyramidal structure. So how can we do that? It can be done based on two ways. Either creating a new or proposing a new network structure that is strictly pyramidal, for example, 3D pyramidal neural network, or imposing pyramidal structure on CNN. So first we will discuss the 3D pyramidal neural network, how it works or what are the key features of this, and then we will go to the second part of imposing pyramidal structure on CNN. So image pyramids or pyramidal neural network are not totally new. They were previously being used, for example, in traditional computer vision by special pyramids, or in neural network by pyramidal neural network. Even in new cognitron and early NeNet follow the same concept, but as the time goes on, they were not strict. For example, some of them use it in only pooling layer, some use it in convolution layer or temporal pyramid pooling, but not in from input till output. By input, the models that use pyramid structure from input till output, we call them strictly pyramidal structure. And Pyramid, as you can see on the right side, is a model that uses back in 2000, it was proposed in 2002. It uses strictly pyramidal structure, but it was only 3 layers. So we call it exactly a deep learning model. But it gives us a hint to use certain features of those models. In addition, in 2013, there was a model called 3D convolution neural network that was proposed. It has a 3D structure. So we took some ideas, inspiration from 3D convolution neural network and Pyramid, and wanted to combine them to have a strictly pyramidal structure with a new weighting scheme that can give us the pyramidal structure also, as well as also reduce the number of parameters, weight parameters in the network. So we call this model a 3D pyramidal neural network. It has a 3D weighted sum or 3D correlation layer, unlike 3D convolution layer, 3D pooling layer, and fully connected layer. The novel aspect on these in this model was its strict 3D structure, 3D weight matrix scheme that is unique, partially shared, locally connected 3D kernels. I will show them in the next slide how these are different than the traditional 2D convolution or 3D convolution. And we have a weight and bias parameter even at pooling layer, unlike the traditional convolution neural network. And even then, despite that we have parameters in pooling layer, we still have less number of parameters than the traditional model. Here you can see the type of weighting schemes. On A shows a fully connected neural network where all the input neuron are connected by a weight parameter to the hidden neuron, and it results in 28 weight parameters in a network. For the same network, if we use the shared CNN kernel scheme, as you all may know, from the kernel you can see green, red, and yellow. This is one kernel that is being shared by all the 4 hidden neurons. And it gives us 6 weight parameters for the same kernel that were having 28 weight parameters. Similarly, we have a third type of scheme that is called locally connected unshared kernels in CNN. So these are the mixture of A and B, mean there is a unique kernel for each hidden neuron, and it results in 18 weight parameters. Then we have a shared partially position-oriented locally connected network where each input neuron has a weight, and those are only used in a kernel when that is in the receptive field of the output neuron. And it shows better far more less parameter than A and C, but still have more than B. But we will see in the coming slide that the recent deep, despite that the recent deep neural network uses B type, that is shared CNN kernels, but as they increase number of layer and kernels, it still have the explosion of parameters, but our model will have far less parameters in the network. Here you can see 2D CNN on the left-hand side. The red or in the middle, you will see that it is a weight kernel, and this is slided over the whole input image of size 5x5. On the right side, we have the 2D pyramid structure or the position-oriented weighting scheme, in which you have the same weight matrix as of the input size. And each time when you calculate an output neuron, you select a position-oriented kernel, and that calculate the weighted sum, as you can see. Similarly, this idea is extended to 3D position-oriented weighting scheme. And in this technique is for spatiotemporal feature learning, and it can be used on multiple clips. So it was the same 2D idea extended to 3D that could be used to different video applications. This is the structure of the model. It is a multi-class classifier. It take a green input image or color now as well. You can take it of 13, 16, as much as you want as input frames. The first layer 3D WS is the 3D weighted sum or 3D correlation layer, followed by activation and then normalization. And in each time, as it is a 3D network, it will reduce, for example, if you take 13 frame as input, it will reduce it to 11 at the next layer, from that 9 in the next following layer, and then 7 in the third layer. And this how the network reduces its dimension in temporal as well as spatial. And in the end, the FC layer will have the reduced most discriminative features in the network that are given to the classifier to provide us output. We use leaky ReLU activation function in this, as well as we have 3D pooling. And as I already mentioned that we have bias for each neuron in the network, even in the 3D pooling layer. The same model, back in 2015, Facebook released a C3D feature extractor model, which extract features and then give the features to a classifier like SVM, and then get the results from that, or you can say simple a feature extractor model. So we took that idea and we used the same model and gave the output of that to SVM to do one versus all classification, the same as the C3D. And we call this model 3D Pyramid F model, and it will show far better result as compared to the other state-of-the-art model. So to conclude, the basic idea about this was to have the pyramid structure that we maintain from input till output. And the second was the 3D weighted sum, or the unique weighting sum scheme that will help us in reducing the number of parameters. Like in the traditional, we increase kernels at each higher layer, but here we are reducing them. We are not increasing. We once select them and then reduce them at each layer to get the most discriminative features at the final layer. We use this model on 4 data sets dynamic scene recognition, Marilyn and UPenn. Marilyn is with a dynamic, non-static cameras. I mean, these are the recordings with non-static cameras, and UPenn are with static camera. For emotion recognition, we use two data set, YouTube and interface. YouTube is a data set is collected from YouTube, and they don't have static background, whereas interface has a static background. The results show that on Maryland, we achieved in multi-class classification. As you can see here, we achieved state-of-the-art result. As well as if we used the one versus all, then we can get even better result than the C3D Facebook model that has 17.5 million parameter, whereas our model have only 0.83 million parameter. And you can see the model that could be deployed on a edge device or FGPA or Raspberry Pi or anything has 305 MB of size on disk, whereas our model have only 14.5 MB of size. So this can help a lot. On interface and YouTube dataset, our model have shown far better state-of-the-art result compared to the state-of-the-art CNN models. This interface is a challenge data set, and yet we have pretty good results on them. So the point here to note is that we have best result, and we have reduced the number of parameter by a huge amount with the pyramidal structure or strict pyramidal structure. Now coming to the second part, how to impose pyramidal structure on CNN. I mean, here we discuss about pyramidal structure in a new model that has a new weighting scheme. So is it because of only the weighting scheme, or is it because of the pyramidal structure? Can the pyramidal structure, if implemented on this traditional or the state-of-the-art CNN models like AlexNet or VGG, will it give the same good results, or will it reduce the parameters or not? So to impose pyramidal structure on CNN, we gave a rule of thumb that if you have a model that is giving, for example, AlexNet, and it is giving you good results, flip it, keep the number of layers the same, but reverse the number of filters. Like if you remember, if we go back, here we have 96, 256, 384, 384, and 256 kernels in each layer. If we reverse that, 256 will come to layer 1, 384 will be layer 2, 384 will be layer 3, and 256 will be layer 4, and 96 will be layer 5. So this is called flipping the kernel in each layer, so that it starts from a bigger in size kernels in the first layer, and then we reduce those by a constant factor f. Mean from each layer we will reduce a constant number of kernels to get a pyramidal structure. This will help us in reducing the number of parameters, as well as it will provide us equal or better performance. For example, here you can see a pyramidal structure of the ImageNet or the AlexNet model. But just to highlight, if the flipping doesn't give you the pyramidal structure, then it will not learn. So you have to redesign them, mean taking the, for example, here we took 384 in the start, then we reduce it by 64, 64, and it gave us a pyramidal structure. It helps in reducing the parameters up to 80%, and it will enhance performance, or will give almost equal performance with less memory consumption on disk. This simple technique can have shown us good result in object recognition, person re-identification, EEG signal classification, and several other applications. Here you can see the AlexNet has 60 million parameters, but we can reduce it up to 40 million parameter without major change in the error. I mean, the top one error was 42.9%, but with 20 million reduction in parameter, we still have the error increase only by 0.3%. Or if we have 50 million parameters, then it has, despite a reduction of 10 million parameters, we have the same error rate. Whereas in this case, we have reduced the top 5 error. There are some other models like sparse memory bounded, AlexNet, Prune, which have, or the recent SqueezeNet, MobileNet, LightNet, that have far less parameters, but they are not inbound techniques in the network. Rather, they are applying new algorithm on the trained models and then reducing them. So a double task, whereas our is a single with simple pyramidal structure, we can have less number of parameters as well as achieve the same amount of performance. So to conclude the imposing structure of a pyramidal structure on CNN, one, it gives a general guideline for the newcomers. For example, if a new data scientist or a new researcher want, a PhD student want to train a model, it's a simple way. Take more number of kernels in the first layer, reduce them by a constant factor, and go on in each layer. And such model will give you some acceptable accuracy, but then you can do slight tuning and that can give you almost equal as of state of the art or better than that. It also helps us in understanding the behavior of CNN as well as in reducing the parameters. We have applied these in different applications, applied on fridge inventory system, cybercrime detection from open social data, epilepsy detection, emotion recognition, and it have shown us pretty good results. So to conclude my presentation, the pyramidal structure give a general criteria, reduce parameters, reduce ambiguity, and this is what our objective in the start. In addition, it provides less memory consumption on disk and can provide easy starting point for new researchers. These are the links to the code if somebody want to use the 3D pyramidal neural network or the network used for emotion recognition. They are freely available. So thank you all. If you have any questions, please, most welcome.
Thank you, Christian. This is Alessandra. A very quick question.
Yes, please.
First of all, very interesting presentation, a really, really interesting line of work. I was wondering while you were presenting, how this methodology compares or shed light into the recent discovery that sparsifying neural network, it leads to much more agile structure with less parameters to train and similar level of result or sometimes even better. So this idea of sparsification seems to me kind of complementary to what you're doing. You're giving a structure to sparsify versus a random approach, or sometimes is based on power law degree distribution to sparsify the network. So there are some statistical guidelines to sparsify network, but the intent at the end is similar to what you are aiming for. So I was just wondering, what's your view on that?
Yes, I mean, that's what our objective was, to give a simple criteria of how to design it in the same, with the same code, with the same libraries that you have, and may get the same results. But the question was how to design these, mean how many layer and kernel should be in each network, in each layer. So the constant reduction of the factors help them in deciding this, answering this question, that how to design it, take large amount of numbers in the first layer and reduce them by a constant factor, so that you may have a pyramidal structure, and in the end you will have the most discriminative features. So rather than trying random number, as you mentioned, in each layer you can have a specific format for selecting them, and yet you will get a good or equal result as of the state of the art.
Very good, very good. So maybe let me try to rephrase just slightly my question.
Okay.
So there are different ways, right?
Yes.
So random, the constant reduction number that you have explored. So those are all alternative way. Your approach is more structured and systematic, which I really like. However, what's the intuition behind that this constant reduction is the right way, is the only way, it's one of the many alternatives? What do you believe? We know that reducing the complexity of those networks still maintain a very strong ability to learn the important features. However, we are only discovering ways to simplify those networks. So you have discovered a very interesting approach. Why do you think we should focus on those kind of approach versus testing a different one, right? That is towards the same goal with a slightly different routine. Do you have an intuition on why this constant reduction may be the right way?
As you are right, this is not the only way, but yes, it is one of the possible way to take start with. If, like as I mentioned in the, like if I am a newcomer and I don't, if I look at this network, there are 96 kernel, 256 and 384. So I don't have an answer why 96 or why 256 or why 384. So there is no proper structure. So our is not like this structure shows good result. Okay, but also the technique or the approach that we have given is one approach, possible approach. As you mentioned, is it one approach or is it the only approach? No, it's not the only approach, but it is one of the possible approach for starters to start with, and may have some good result on a data set. And the second most important point is, if you have a network that is giving you, which is not in pyramidal structure, but giving you good result, but when you want to deploy it on, for example, an edge system, or for example, Tesla cars, they have to regularly update their systems, mean the system in the car. They have regularly updates their system. So they have to transfer the new model to the car. Okay, that was one of the intuition initially behind that. So if they have to transfer and the model size is big, there are chances that it can be corrupted and it might not reach correctly to the system, or it will require more bandwidth. Or for example, in the fridge inventory system, we have this, that there are hundred of thousands of fridge where we have to transfer these models to update them. So how we can do that? and it is not necessary that these models will be in areas where the internet is good. So the smaller the model, that will go faster or downloaded faster. So in that case, if I have, for example, this LXNet, and that is acquiring 256 MB, but I can get the same accuracy in, for example, instead of 256, I can get it in 100 or 50 MB. So it reduces the chances of corruption, as well as when there are embedded chips and they have limited memory, they can get help from this reduction of parameters. So it is not the only way, but it is one of the possible way to have lightweight networks. Does it answer your question?
Yes, it does. Thank you.
Thank you. You're welcome. Do we have any other question?
Hello, Ihsan, it's Eren.
Yes, sir.
I'm just wondering, on the architecture, I saw additional function before output. Actually, it was SVM support vector.
Yes, yes.
Just wondering, maybe there's a research on this topic. I think so. The output, that's my feeling, linear, or I'm not sure, maybe non-linear. It depends on the data set. But I'm just wondering the kernel in terms of mathematics side. Is it exact function in terms of kernel on this architecture, or is it changeable? Because I believe that it might be changing the accuracy.
You mean the SVM?
Yeah.
No, what we did here is we take the features with the train model and give it to the SVM.
Yeah, so the
and
one
we,
of, yeah, the one of,
and it is one,
yeah.
The one that we used was linear classified.
Linear, yeah? Okay,
Yeah,
so it
yeah.
was like linear.
It was, yeah, linear classified, yeah.
Okay, thank you. Just this question.
Yeah.
So I'm just wondering, is it changeable to?
Yes, you can use, I mean, you can use random RBF or non-linear classified as well.
Okay, thank you. Thank you for this.